So we have interrupts. What is an interrupt? So interrupt is an actually interruption to the normal execution of the program. So basically when computer is doing actually one task and suddenly there is another task that needed to be done. Okay, and that is called interrupt. So let's assume now you're taking the class and suddenly there is some emergency at your home. So what you will do, you will actually stop, you will actually go away from the class and actually do that. Okay, so interrupt is something like that. So in a computer there is actually multiple program running at the same time, and CPU can actually work with one program at a time. So CPU, the central processing unit, is working with one program. So suddenly another program or another instruction, okay, needs some urgent or emergency help from the CPU. That means it need to actually complete some emergency task. So what will happen? It will say interrupt. Okay, it will interrupt the current program and actually do that task. So let's first go to the definition, then we'll see the diagram and it will be make more sense. An interrupt is a signal from a device attached to a computer, or this is number one, or from a program within the computer that causes the main program that operates the computer, the operating system, to stop and figure out what to do next. So let's break the definition again. Interrupt is a signal. That signal can come from a device that is attached to a computer. That means it can come from a keyboard, it can come from a mouse, or any other devices that is connected to the computer. Or that signal can come from a program within the computer. So it can be come from, suppose, your Facebook. Okay, suddenly you have a notification. Okay, so we have seen the notification can pop up under your screen. Suppose you're watching a movie and suddenly you will see a notification under your screen. Okay, or it can actually come from any other main program. Okay, and what it will do, it will cause the main program, that is operating system, to stop. So let's assume the operating system was working with one software or one program. It will make the operating system stop and figure out what to do with next. That means it will say, okay, stop now. Okay, here I have another issue, solve it. So operating system might decide to solve it in that moment, or operating system might decide, okay, wait, I will solve you later. Okay, so that is interrupt. Now, an operating system is interrupt driven. So what does this mean? That means whenever you're actually running an operating system, when there are multiple tasks to be completed, okay, so operating system actually depends on the interrupt. So that means whenever operating system is executing one task, okay, and whenever another task is needed to be executed, operating system actually depends on the interrupt. That means operating system doesn't go away and look for everything. Okay, that person comes to him. Let's assume that this class is interrupt driven. What does this mean? That means suppose I am the operating system, I'm teaching you the topic, and if you don't understand the topic, I am actually waiting for your interrupt. That means you will either ask me a question or raise your hand, and then I will explain the topic again. Or otherwise I'm thinking, okay, everything is going fine. So just like this class, operating system is interrupt driven. So whenever you're running multiple programs or running a program, if some emergency occurs, okay, that another program or another device, they can actually raise an interrupt. Just like the way in this class, if you have any confusion whenever I'm covering a topic or slide, you can actually raise your hand or actually interrupt me. Sir, I have a question. So that way actually this happens. Now, what is the reason we actually depend on the interrupt? First of all, it is efficient. And secondly, it improves the processing efficiency. Okay, so the same point, by allowing the processor to execute other instruction while an input-output operation is in progress. So this is one example. Okay, remember the one that we have learned a little bit ago, the interrupt-driven I/O. So this is another example, you see, of how interrupt occurs. So here, as you can see in the interrupt-driven I/O, what happened? So normally in programmed I/O, CPU actually asked input-output device for input and it waited. And when the input output was ready, it let the CPU know and the CPU kept progressing. But in interrupt driven IO, what happened? That whenever actually CPU needed an input, it actually gave the instruction, the command to IO module, and it started doing some other tasks. And when the IO module was done, or the IO module was ready, okay, what happened? That IO module actually told the CPU, hey, I'm ready. Let's go for the next step. So this is called interrupt, okay? So overhead required to service the interrupt. So what does this overhead required to service the interrupt means? So first of all, let's see what are the overheads. Saving current context, deciding of the code to handle interrupt, and switch back. So 3 points. saving current context, deciding of the code to handle interrupt, and switch back. So what does this actually mean? So let's see. So suppose we know that any program is actually collection of instruction. Okay, so let's say this is a program. Okay, this is a program A. It has instruction from 1 to M. So we have seen in the instruction cycle, what happens? We fetch one instruction, let's assume instruction 1, we decode instruction 1, and we execute instruction 1. Then after being finished with instruction 1, we go to the next instruction. And that's how the computer's instruction cycle work. We have seen in the last lecture. Fetch, decode, execute, and then we actually go back to again to fetch another instruction. Okay. Now, when we have interrupt, what happens? That suppose you're executing instruction 1, 2, and 3 and goes on up to I. Okay, let's assume the value of I is 6. So you actually finish up to instruction number 6. Okay, good. So what's next? So when an interrupt occurs, what the computer do, okay, or the CPU does, you see CPU was executing some task, user uses the keyboard to issue a high priority command. That means an interrupt. Okay, the issue an interrupt request to the CPU. So whenever you give a high priority command, that issues an interrupt. Okay, CPU suspend the current execution of the program. That means CPU was doing program A and suddenly there's a high priority program B that needed to be done. And the command was requested by the keyboard. Okay, and what the CPU does, it was instruction number 6, it suddenly sees that there's an interrupt here. So that there's a notification that comes to the CPU. You can see the arrow sign. Okay, let me just move it, make it more clear. So this is, let's assume this is 6. And you see there's suddenly there is another interrupt that, hey, there is another more high priority task that you need to do. So what the CPU will do from this position, it will actually finish the instruction number I and then it will go to B. Now, after finishing B, it will actually come back to I plus 1. So if we are executing instruction number 6 and then the interrupt came, okay, suppose you were executing instruction number 10, then the interrupt came. So what you will do, you will first finish instruction number 10 and after that you will go to that program B, you will finish B and you will actually come back to I plus 1, that means 11th number instruction. So this is basically something like this. Whenever interrupt occur, we pause a program, okay, we go and do some other task and we actually resume the program. Now, the problem is this pause and this resume is actually not that simple. Okay, so we actually need some process or steps to actually handle this. So let's go back to some previous slides. So as you can see, as I have told you before, that the CPU has different register and program counter, IR, MAR. So whenever you are executing a program A, all of these have their own value. A has a own program counter, A has its own instruction. Okay, so whenever suddenly another program comes, okay, first one you need to do, you need to actually copy all this data of program A. You need to copy all this data and you need to store it somewhere in the memory. And then we load B into PCIR, because whatever the program is, we always need these registers. But in a computer, we have only one CPU. So a CPU cannot execute both programs at the same time. So what it does, it actually pauses A, it copies all the data of A and save it to the main memory. And then from the main memory, it actually loads the B, it executes B. And after B is done, it actually sends the command, okay, B, you're done. A, you can resume. Then A actually copies all the information back to the CPU. So basically, when A is paused, all the information of the A is copied to the main memory. Then we load B, and after B is finished, we actually load again A. So this is called the overhead of interrupt. That means whenever you are using interrupt, you need to do all this extra task. You need to actually store all this extra memory. So these are called overhead, or the problems with the interrupt. So saving current context, you see the PC, the IR that I'm talking about, these are falls under the current context. Deciding of the code to handle interrupts. So whenever an interrupts occur, you need to specific bit of code, how to actually handle the interrupt. Okay, whether you need to copy the data, how to load the data, all this actually needs some another software, another code. And then after your interrupt is done, that means B is done, you need to switch back. So this is called overhead required to service the interrupt request. Now, what are the types of interrupt? There are 4 types of interrupt: program interrupts, timer interrupts, IO interrupt, okay, and hardware failure interrupt. So that means these are the reasons an interrupt can occur. So it occurs when some instruction within the program creates a condition that leads to an interrupt. So basically, whenever you're running a program, you actually divide by 0, or there's an arithmetic overflow, or attempt to access an illegal memory. So some different condition actually issues that interrupt that comes from a program. It might be due to an error, or you actually might need some information. So those are the reason a program interrupt can occur. Then there is timer interrupt that is generated by a timer within the processor. So timer interrupt can be, suppose your computer need to be updated after 1 week, every week. So a timer will be set for update function. Automatically it will, after 1 week, it will send an interrupt that I want to update my computer, and automatically it will be updated. Or another example can be, you have an antivirus that need to check your computer daily at least once. So that means every day at a certain time, it will give an interrupt and it will stop whatever you're doing, and it will actually run the antivirus. And then there is IO interrupt. Whenever you need to take input from the user, or you need to take other signal, we use IO interrupt. And then we have the hardware interrupt. And hardware interrupt means suppose there's no power failure, there's no current, there's no memory parity. Okay, so due to some hardware issues, the operating system might also stop their work. So keep in mind, all these types of interrupt, they do one common thing. They stop the operating system from its current execution, and then operating system has to decide what to do next. So for the program interrupt, operating system takes one type of steps. From timer interrupts, operating system takes another type of step. IO interrupt, it takes another type of step. Now there is a question that might be, sir, that you are saying that operating system work with one software at a time, but in our current computers, we can actually run multiple software at the same time. Even I am right now running an PowerPoint and Zoom at the same time. So that means, where is the interrupt? Okay, and we can actually run multiple software at the same time. And how the interrupt occurs? So basically, we are first learning for a computer that is very basic. Okay, now the computers we have, they use a technology that is called pipelining, so that multiple instruction or multiple programs can be run at the same time. Some of the computer are multiprocessor, you have heard the name. That is, they have not only one CPU, they have multiple CPU. But for our easier understanding, we will first study with one processor that actually is not that powerful, and there is no pipelining condition. Okay, now let's go to the next. That is, let's come back here. So as I was saying, CPU was executing some task. User inputs the keyboard to issue a high priority command. CPU issues an interrupt request and suspend the current execution. CPU executes the code written to handle the command. So that means to issue the code that is needed to handle the interrupt. So there is a name for it. We call it ISR, interrupt service routine, ISR. So we'll study in details what is ISR in the upcoming slides, chapters, and then CPU resumes its previous execution. When we're done with B, it comes back here. So very simple, right? Now, previously we have seen instruction cycle. Now we will see interrupt cycle. So what is an interrupt cycle? So basically this is the same as the instruction cycle. If you look closely, just we have this extra part. This part is same as the previous figure. If you go through them, but now we also already added an extra part. This extra part is for interrupt. So what happens now, after you fetch the instruction, you decode the instruction, you execute the instruction, you check whether there is an interrupt or not. So that means, suppose you are executing a program with aim instruction, you executed 1, and then you check, okay, I am done with instruction number 1, whether there is any other instruction or not. Then I am actually instruction 2, 3, and it goes on like this. So if the interrupt is enabled, it actually checks for interrupt and actually handles the interrupt. And if the interrupt is not enabled, it actually goes back to the normal instruction cycle. So this is we call interrupt cycle or instruction cycle with interrupts. You see the name 1.7. So let's see how the interrupt processing actually takes place. We have already seen a diagram here that how actually we transfer the control from A to B. Now we will actually see some more details. So from the hardware part, device controller or other system hardware issues an interrupt. So it might come from a software. We have read in the definition that interrupt is a signal that may come from any devices or programs. So device controller or any other system hardware issues an interrupt. Okay, processor finishes the execution of current instruction. You see, suppose processor is working with instruction number 10, it will finish 10, and after that processor signals acknowledgement of interrupt. That means he will say that, okay, I got the interrupt. Okay, that is called acknowledgement. So suppose if some of you raised your hand and I will say, okay, suppose Sakib raised his hand, I will say, hey Sakib, okay, I see you. That is called acknowledgement. Okay, that means I will let you know that I see the interrupt. And when processor pushes PSW and program counter into the control stack, that means it will copy all the data of the program it was currently executing and stored them into the main memory. You know, remember the picture I have shown you, that this is the CPU, this is the main memory. So let's assume CPU was executing A. So whenever the interrupt occurs, CPU actually copies all the information to A. So this is what has been done here. And then processor loads new PC. That means processor loads the B, the new instruction address program counter, and then save reminder of the process state information. Then process interrupt, it completes the B, and then after B is done, it again loads the A. So basically this diagram and this diagram is almost same. Okay, just this is in details. Okay, we divide into hardware part into the software part. Now PSW means program status word. You see, it is a part of control registers. If you don't remember, go back to the previous slide. Now another topic, that what are the types of interrupt? We have seen there are 4 types of interrupt: program program interrupt, then we have the IO interrupt, timer interrupt. Okay, but apart from those interrupt, there is another case we need to actually be concerned about. So what is called? It is called multiple interrupt. That means you are already handling one interrupt, okay, and then suddenly there is another interrupt. So what you will do? So basically think like this: you are running program number A, and suddenly this is your program number A, suddenly there is the interrupt here. Okay, so you actually stop your program number A and you go to program number B, because B has now interrupt. So and you start working with program number B, and then suddenly there is another interrupt, that C. So what happens? You will stop B and you will go to C. So this actually becomes complicated very soon, because in a computer we actually run multiple programs. So what happens if each program keeps sending interrupts one after another? Okay, the computer actually gets very confused. Okay, and it actually, the amount of data that being transferred from main memory to the CPU actually increases, because you see, if I was working with A, then if the B came second, all the information of A needed to saved into the main memory. So then suddenly another program C came, so all the information of B was needed to save into the main memory. So this becomes actually very problematic. So the computer scientists had to find a way how to actually handle this interrupts. That means if we have multiple interrupts at the same time, what can you do? So there are 2 choices. One is disable multiple interrupts. That means you will not actually take multiple interrupts. What does this mean? Suppose you're actually running program A and suddenly there is an interrupt. That interrupt is program B. So whenever you are actually handling program number B, the system that can give the interrupt, we call interrupt handler, it will be disabled, so that it cannot give any more interrupts. So when you are finished with B, okay, and you're again back to your main program, it will be possible to give interrupt. Only then the C program can give the interrupt. So again, what is the first choice? That you will disable the interrupt handler, that handles the interrupt. Okay, whenever you are handling one interrupt, it will be disabled. Another is sequential execution of interrupt. So what is that? Suppose you're executing program A again and there is another interrupt B. So when B was happening, there was another interrupt C. So what you will do, you'll actually make a line. Okay, so we have B, another interrupt. Okay, so we are processing B, then there is another C, then there is another D. So all of them have to wait in line. Okay, so if they wait in line, what will be done? Okay, after B is finished, instead of going back to A, what we will do, we'll actually go to C. Then after finishing C, we'll finish D. After finishing D, we'll finish E, and then finally we'll come back to A. So in short, in sequential interrupt execution, what we do, we actually start the user program, we handle X, one interrupt, and if there is another interrupt in that time, we actually store them in a line, that wait in a line. After I finish with X, I will go for Y. And we keep going on like this. And another way is that priority scheme. What is a priority scheme? So basically priority scheme means that each program will have an priority. So that means if you want to take input, it will have a priority 5. If you want to print something, it will have a priority 6. So these priorities are assigned for now. Let's assume that they are assigned by the CPU. So computer assigns the priority for different programs. So whenever an interrupt will come from a program, okay, each will have their priority ID. So let's assume X. So we're running, again, we're running our program A, and then there is another interrupt came B. So instead of directly going to the B, what the computer will do, it will first check what is the priority of B. If B has more priority than A, then it will go to the B. Otherwise, it will actually stay in the A, it will finish A. Same goes for B. Suppose it is executing B and suddenly another program came C. So what the computer will do, it will check whether C has more priority than B. If yes, then the program will stop B and go to C. So that's how actually we can use priorities. So the lower priority handler, we can interrupt the lower priority from higher priority. And another example that can be that when input arrives from a communication line, it needs to be absorbed quickly to make a room for more input. So that means it's more higher priority. So we'll actually execute that first. So these are called multiple interrupts. Okay, so basically we're done with multiple interrupts. So we have just one slide left, and then we're done for today. So before going to that slide, do you guys have any question? Program flow control. So what is a program flow control? So now we will see how actually program actually runs in a computer. And first we will see without interrupt, and then we will see with interrupt. So let's assume I have a user program that has 3 parts, part 1, part 2, and part 3. And if I want to take some input, I have to run a portion of the code that is we call part 4 and part 5. So first of all, any input output program consists of 3 sections. Okay, a sequence of instruction that we labeled as 4 to prepare the actual IO operation. That means if you want to take the input, okay, the first step, okay, the A is a sequence of instruction, okay, that will be preparing for input output operation. So it might be include copying the data to be output into the special buffer or preparing the parameters for a device command. So let's give a short example that if you want to actually run a program that you can actually input as 2 numbers. So first step is to make sure allocate the memory and before running the program and declare the variable. Step 2, the actual input output command. Without use of interrupts, once this command is issued, the program must wait for the input output device to perform the requested function. Program might wait by simply repeatedly performing a test operation. So basically the second step is, so when the program is actually taking input from the user, okay, the processor, okay, it actually has to, or the program, it actually has to wait until the IO is finished. And finally, step number 3, a sequence of instruction level 5 to complete the operation. This may include setting a flag indicating the success or the failure of the operation. So these are the 3 steps of IO program. Whenever we are trying to take input, we have to complete these 3 steps. Number 1. Now, number 2, let's go back here. So we have a user program. After step number 1, what do? We need to write something. That means we need to take some input. So we go and complete step number 4 and 5. And then we come back and again we start doing our task. And again, whenever we need to take some input, we go back and complete step number 4 and 5. And what is the step number 4 and 5? The process of taking input or IO operation. Okay. Now, how we can actually optimize this? So we can actually optimize this using interrupt. So what does optimization mean? First of all, you can see whenever I'm taking input, computer actually prepares itself, then it takes the input, and then I can actually resume my work. So all this time, this is actually sitting idle. It's not doing any work. Okay. So what do we want to do? That we want to use the interrupt service here. So what will happen? We'll start a task. We'll go and say, hey, IO module, give me the input. And then we'll come back. We'll not wait for IO module to finish its task. Okay. So meantime, IO module will say, okay, I have this task to do. So you say I will finish step number 4, I'll step number 5, and when step number 5 is finished, only then it will again call that, hey, I'm done with taking the input, come and take the input. So basically what happened previously, we waited for step 4 and 5 to be finished, and then we actually resumed our task. But here, where after step 4 we are coming back, we are doing some other task, okay, we're actually making progress, and then after step number 5 is done, we're actually coming back. Okay, it's giving an interrupt that, hey, I'm done with input. So control is transferred to the program, and then we again resume. So let's see here again, after 2B, we again have another write operation. So we again first go to the step number 4 and come back and start doing some other task. And after the input is done, we actually notifies us in this cross section. So this is the advantage of using interrupt. That means you don't have to sit idle. So another example that it will be easier for you to remember. Let's assume you went to order food. Okay. So previously, what you had to do, you had to actually go to the restaurant, order food, and you had to wait there until the food is being ready. So you are waiting there. Okay, so 30 minutes, 1 hour, and after it is ready, you are bringing back the food. But now what you are doing, you are just actually going there, you are ordering the food, and you are leaving. And when the food is ready, using an interrupt, it actually giving you the service that, hello, sir, hello, for example, hello, Mr. X, your food is ready, now you can come and take it. So this is obviously much better, right? Because previously you had to wait, now you actually don't have to wait. So that's how actually the flow control works. So today we'll finish here. Our chapter 2 is